Welcome back for those who joined us yesterday, and welcome for those joining us for the first time today. We have a great selection of presentations yesterday, and today is going to be the same from the market-leading professionals in your industry. You can choose between the security dome here or the main hall, from the agenda you've been given, and take the chance to network, check out the stands in the common areas of the building, and there may be some places in the workshops if you're interested in that. Sit back, relax, enjoy your day. Our first speaker today, welcome to the stand, Mr. Márton, Illés.
Thanks very much. Thanks for having me. And good morning, everybody. And welcome every early riser. Today, I would like to talk about firmwares and basically talk about how we can extract firmwares. But before we begin, I'm just curious, has everybody ever worked with firmwares like reverse engineering or doing any security analysis? All right, it's good. All right, so then hopefully I can show you some interesting insights into that. So let me just quickly jump on it. I'm working for a company called OneKey, and basically what we are doing is automated firmware analysis. And what I would like to present to you today is a new open source tool, which is called unblob, which was basically born from the problem that we were facing by working with firmwares. In any firmware analysis or any analysis, the first step is always like, I have a firmware image, I don't really know what it is, and I somehow need to unpack it. If it's a Linux system or maybe another system, I need to somehow extract it. And the problem we were facing that there are so many tools out there specific to one firmware or one format, and we have to always like figure out like, all right, this firmware is by this vendor and I need to use this script. And if it's another one, I need to go to GitHub, I need to pull another one, and I need to figure out how to extract the firmware. So basically what we were looking for is a tool that we can use in an automated way, or a semi-automated way at least, which will do all this work for us in an efficient way. So basically we wanted to create a framework to extract firmware. And we created unblob and open sourced it. It currently has support for over 30 formats built in, it's counting. And basically it can handle different archive formats, like the traditional one, starting from zip or tar files. It can do different types of compressions as well, and a bunch of file system format that you typically see in embedded or IoT or OT or IIoT or whatever buzzword you want to choose in the life. When we started to work on unblob, we wanted to basically find something that can deal with arbitrary formats. In many cases, the difficulty is like figuring out like what the format itself is and dealing with the problem that many firmware images have what I would call like a matryoshka format, where there is different layers and layers and layers, and you might unpack one and then you face another one, and we wanted something that we can just work on it, work with arbitrary formats, and work also with untrusted format. It's very bad, and we have seen cases where there are some malicious thing in the packing. Just think about like zip bombs and stuff like that. So basically, when we set out on this journey, and I will show you today in details, we defined a few objectives we wanted to achieve. So we wanted to have a tool that's very accurate. In any analysis that you might have conducted, or from our experiences, that if we are not accurate, then basically we are facing with this garbage in, garbage out problem. If we have a firmware, we extract it, and it produces a lot of garbage, then any further analysis I do on top of that, might it be some manual analysis, some automated analysis, or an emulation for that matter. But if I get a lot of junk, it makes my life very, very hard. The second objective, obviously, we are dealing in the field of security. We wanted something that's not introducing too much of an attack surface. So we want to make sure that the extraction process is as secure as possible against things like zip bombs or path traversal attacks. Also, it was very important that we envisioned a tool that's very easy to extend. A lot of us in the reverse engineering or in the security community, when we face a new format, we just write quickly a script and then maybe push it on GitHub if we are cool, or we just forget it somewhere around our hard drive or God knows where. And then the next time we face the same problem, we might remember that, oh, I had a script, maybe I just rewrite it. But we wanted to create something that I can, as a researcher, very easily extend and add a new format. So at the end of the day, I will have a library of all the formats and in one tool which can unpack all these files. And last but not least, sometimes we have to deal with large firmware or a lot of firmware. So we wanted something that can actually perform well and not too slow at the end of the day. It's not like we are talking about milliseconds or seconds, but it's good if we can get results in minutes. So these were basically our objective when we set out. It was very funny when we announced that basically we get some results. We were using also Bimwalk, and basically we wanted to something like this, like Dave mentioned it, this is something like Bimwalk wants to be when it grows up. So it's also like a replacement for that. With that said, what I would like to talk about today is basically just give you a very quick introduction to the tool Unblob, quick getting started, jump into some details and show you how the extraction and analysis is done. We have some cool reporting features built in. I would like to showcase that. And what I'm planning to do today to show the extensibility and also welcome everybody to contribute to the tool is show you how to create a new format handler, which can deal with a format that has not been supported before, and also show you how that format can be extracted. So that's the plan today. I don't have too many slides, and I will jump on the demos. But first thing first, let's see how to get started with Unblob. Even before that, big kudos to the team who actually helped to create it. And again, I would encourage everybody to contribute. I'm very happy to put any of you on the slides next year. It would be so great. All right, so basically, there is 3 ways to install Unblob, and we wanted to make it super simple. One is that we created a prepackaged Docker image that you can just pull it and use it. So there is no need to install any dependencies and whatnot. I think this is the easiest way to use. The second one is to use Nix. I'm just curious, anybody's using Nix here? Okay, anybody knows Nix? So if you haven't used Nix, check out. It's an awesome, cool dependency management system. Basically, I would say on package management, the best thing since sliced bread. So it's really cool. It's a cool thing. And of course, the third way to deal with Unblob or just to get the source, it's on GitHub, and just install all the dependencies yourself. So as said, with Docker, it's super simple. We are publishing basically always from the master branch a latest Docker image on GitHub. And all you need to do is just run it, volume mount, the source directory, the destination directory, and everything else is taken care. Also, if you are using Nix, you just need to install Nix, and then all the dependencies are automatically installed and pulled in. So you don't need to figure out one by one, like, oh, how do I install my LZIP decompressor or tar or whatever tools we are using to do the actual extraction. And of course, if you want to go to the source, just clone it from GitHub. We are using Poetry for dependency management. So basically all you need to do is just run Poetry install. You'll get the base, but it also means that you need to manually install all the extraction. So with that said, let's extract some stuff. So, all right. So I would show you, obviously on my laptop, I have everything installed. I hope you can, let me make it a bit bigger so everybody, even in the last row, can read it. Using it is very, very simple. We have an extensive help page describing it. You can read it if you get lost, but nobody reads documentation, as we know. So running it is super simple. You just need to define what is the extraction directory. I will just pick a directory. And then you need to specify a firmware image. So I prepared a few image. Let's start with an OpenVRT one that's fairly simple. And basically what it does, it goes through the file and does the extraction. And if I go I'm very old school, so I would use Midnight Commander. Then all the files are extracted. So basically, you can see that here is the OpenVRT extract, and it got extracted. It basically tries to find some chunks in it and then goes through all the extraction process. So first it detected that there is some gzip compression, then it extracted it, then it went forward with the content, what's inside gzip, and extracted it. It detected some file system, in this case some X file systems, and I can go there and all the files are there, and I can work with all the files I need. So it's super simple. The power of Unblob that it's not just trying to blindly unpack everything and try to find everything there, but it tries to be very precise. One of the goals, as I stated in the beginning, is accuracy, which means also that there are certain cases in files where we encounter unknown chunks. Sometimes we detect that, hey, here is a file system, this is how long it is, and there is some data after that. So we are trying to also flag these unknown chunks and also carve out from the files, so maybe it can be analyzed later. It might be some padding, it might be some digital signature in some cases, or it might be just some format that Unblob is currently not supporting. So we give the chance and try to be very explicitly what we can deal with and what we cannot deal with. So if I just go there, you can see it's actually a group boot record, which we don't handle right now. But you can also go to the end and see that it's probably some padding at the end. We are planning to add, obviously, more support for these, but we are trying to be very explicit on what can be extracted and what cannot be extracted. Another cool feature of Unblob is not just that it can extract the data and extract the files, but it can also report on what it did find and what it did not find. So let me just override the previous file and add a report to it. So basically everything we detected can be written into a report. So let me just quickly rerun it. And then I have a JSON report. I'm very bad with report. So basically, I get a very detailed understanding of like what we extracted. If there are any files that we identified, we are also reporting on the size, whether it's a file. We are also reporting on every file if we detected the hash information, and also we are reporting the unknown chunks, stating what are the start offset, end offset, size. So we try to give all the information. We also created a very simple tool. Let me just quickly switch there. Oops, I'm just using Jupyter, where we can basically load this report and generate a chart which can visualize how the firmware is actually built. So this sunburst is actually representing the different layers of the firmware. If I move there, I can read the details. I can see what was the file size, where the actual file is, and I have the ability to zoom in. So if I'm interested, I can see different layers. Let's say I'm interested in the big one. So I just double click on it, and I can precisely see like what is included in the file. So this is just a simple one to get me an overview of what we identified. It's also very cool. Let me show you, because some people might prefer other ways. Instead of a sunburst, you can also get a tree map and see like what the contents are. So it's very easy to very quickly identify what's lurking within a firmware. Also, you can very quickly see like if we identified a unknown chunk, where it is located in the file, what is the size. I did not put it here, but we also calculate the entropy of it, so you can get an understanding whether it's maybe compressed or encrypted, or maybe just the padding if the entropy is very low. So hopefully this gives you a tool that helps with the extraction process. With that said, let me just jump back to the presentation and talk a bit about how Unblob works under the hood. So basically, the way how envelope is constructed, that it is scanning for certain format patterns. Every format handler can define a pattern, which is usually some magic or some pattern that we can search for. We are using Hyperscan, which is a very cool library from Intel, which is a super fast regex matcher. So we are using it to find patterns within the file. Once you find a pattern, then basically the handlers which are specific to a format, they are calculating the size of the chunk. So if I have one big binary files which might have, let's say, multiple file system packed in it, maybe packed after each other, maybe there are some paddings between that, then the handlers through the pattern can pick up those chunks. And then based on the chunk content, we can calculate how big the chunk is. So we exactly know where the start of the chunk and the end of the chunk is, so we can carve it out. So we are basically carving out all the chunks that we identified, and we are also carving out all the leftovers, which are basically the unknown chunks in the game. Excuse me. Now, once the carving out is done, we can use the extractor. The reason why we do this carving out, that we, in some cases, you are using some external extractor. For example, if it's a zip file, you're just using, for example, 7-zip to do the actual extraction. But 7-zip does not know how to unzip from a file and an offset within a file. So we need one file which is itself a zip file in this case. So we have the carves, we are extracting it, and we are calculating the entropy for the unknown chunks, and then basically recursively iterate through all the extracted files to handle this Matryoshka problem to deal with any embedded or other layer of operation. So this is the high level. Now the architecture and just a few words on the architecture. The architecture of envelope is super simple. We're basically providing you a core. Again, everything is open source here. The core provides it as a CLI, so it's the command line tool, which I just shown you, but it's also available as a library. So if you want to embed it into another Python project, because envelope is implemented in Python, then you can do it as well. Also, the core provides the pattern matching and the chunk carving functionality, so you don't need to implement it. And it also provides a plugin management. Basically, you have the option to define plugins, and plugin contains the handler for different formats. And if you are developing, you can just create your own repository, put into a plugin, say, my handlers, and then this plugin is automatically loaded. All the handlers from the plugins are loaded and are used throughout the detection and the extraction process. Also, the core provides logging and reporting capabilities, just I showed you before, and it provides a ton of useful utility functions. So when you are dealing with different formats, I will show you right away, then we are trying to give you small tools to help you with the parsing or conversion and other utilities that might come handy, which is usually re-implemented all the time if you are just writing your own script. Now, the envelope handlers are, I would say, this is the core. So envelope handlers are the brain of the core that makes envelope super powerful. Basically, handlers can be defined, as I said before, in plugins. So it makes it super easy to extend it. You don't necessarily need to open source it, or you don't necessarily need to upstream your handlers to keep it easily manageable. Of course, you are very happy if you do so, but you can keep them private if you want. And the goal of the format handlers that they are responsible for the chunk calculation and the chunk detection, and also the extraction. So all the format-specific logic stays within the handlers. So that's on the high level, the architecture. Just a word on the extractor, because that's also a very tricky thing. From our experience, it's usually easy to identify a certain chunk, but extracting it is sometimes much more difficult. Just to give you an example, for example, squashfs, which is very commonly used in different firmwares. Actually, finding a squashfs and understanding the length of it, so the basic chunk, is not super difficult. But extracting it is not that trivial. So for example, we are using Sasquatch to do the job. Now, unfortunately, Sasquatch was not very well maintained, so we decided with a bunch of extractors to fork them and actually start to improve on that. So if we have a Sasquatch fork, we have a Jefferson fork, UB Reader, JeffSheaf fork, and we are trying to also fix bugs and add support for other formats, because some of the vendors get very creative on dealing with formats and they are extending in the way they want to deal with. So I would also recommend to check out some of the forks. We try to maintain it. If there are any problems, try to fix it. We are also heavy users of all these forks. In case of some easier format, which is easy to implement, or there is no tool available, we just decide to build it as an extractor. But it also means that you have the chance either to use some tools that are readily available, or you can create your own extractor as well. So let's jump into that and let's try to create our first extractor. Before doing so, I just picked up a firmware. And this time I decided to pick something simple. So I just picked up a Netgear firmware, an R7000 whatever. I just downloaded it from the internet. And if I run an extraction on it, then it does the extraction. If I go to the results, let me just quickly go there. I can see that here is the result. And generally it's extracted. I see there is some squash effects in it, which we detected. There is some LZMA file. I can go into the details, see what it is. Oh, it finds a dev, console, root, so it's probably a Linux kernel that we detected here. But generally there are a lot of unknowns. And I just picked this very, very simple one. If I look at it, you can see that it's actually a CHK format, which is specific to Netgear. So for this purpose, I just want to understand this header information and see how we can deal with it. So in order to conserve some time, I actually pre-coded it yesterday. And I just created a handler for it. So here is envelope. Here you can see all the handlers. And I created, hopefully I will be able to find it, a Netgear handler. So this is basically how a extractor looks like. Let me try to zoom into it so you can actually see it. Okay. Okay, let's go back to the command line. It's always better. So this is how let's use VI, that maybe they'll do some color enhancement. Yes, much better. So actually doing a handler is super, super simple. This is basically how a handler looks like. One of the important things that you need to define is you can define a pattern that you want to search for. So this is basically the pattern that will be searched. This is the magic at the beginning of the file. If you recall this 2.8, 2.3, 2.4, 5e, this is basically the magic for this file format. So by defining the support for this format, I just define like what is the pattern I'm looking for. And the other thing that I need to implement is basically the chunk calculation. So it's a callback. Once a pattern was identified, then this callback is called, and it's past the file and the start offset. And all it needs to return is basically a wallet chunk type, where I need to specify like what is the start offset, which is usually simple, and also what is the end offset. In order to do so, what I need to do is actually parse the header. And what we are using is also a struct parsing. It's very, very common that some structures are available in the source code. So in this case, what I did, I just copied a structure definition, which basically defined this format. As you can see, there is some magic, header length, some reversing, which might make sense. I don't care because it's not required for the unpacking. And there is a kernel and a root file system lengths in it. There are also some checksums. So if you want to be super precise with the extraction, you can also do some checksum calculation. And then basically I can define that I'm using this as a definition, and then I'm just parsing it. So we are trying to provide all these utility functions, so actually creating the handler is super, super simple. In this case, I know it's a big endian. We can also do and have some utility functions to do some endianness detection based on some logic. And then I do some calculation, just to be sure I'm logging the header, and then I'm returning the identified content. So let's quickly run it again. And I'm just adding that I don't want to go very deep. Maybe I want to go a bit more verbose. So in this case, I can see that on debug level, we identified the header. We also have some utility function to make it super nice color-coded if we parse the header, so you can very quickly see if the header is correct, like what are the details in the header. So in this case, I can see the board ID and all the other fields as well. That's basically how I can identify the chunk. There is also the log on like what the chunk that I identified. We also have some speed improvements that, for example, if we identify that the chunk covers the whole files, we start searching for other chunks. So it's super simple in that way. Now this is the first step. The next step is that I need to actually extract it. Now in this particular case, the format is very simple. So let me jump to the next step. Load. Where I have added an extractor. So basically every handler I can define like what the extractor is, where the extractor is responsible for actually extracting the carved out chunk. In this particular case, there is no external tool, so I just decided to write my own extractor. So let's see how complicated an extractor is. That's pretty much the extractor. Again, logic is very similar. We are using the struct parser. We can use the same definition that we used before. And basically, the extractor gets the in-pass, the carved out chunk, and gets a directory where the extraction should happen. So all we need to do is just parse again the header. We wanted to separate the chunk detection and the extraction, so we are trying not to pass information to keep the API simple and clean. And all we need to do is just seek to the end of the header, and we know that there is a kernel and a rootfs. I just created a super simple function which will dump it into a file. We have this function readily available to carve a chunk to a file. So I'm just defining that, okay, here is a chunk, which in this case will be the kernel or the rootfs with the defined lengths, and then it will do all the extraction. Let's see how it works. So in this case, also going forward, this is where I can see that the charge was counted out, and as I defined a maximum depth, it does not go in, deeper, so it stops there. So let's quickly see. In this particular case, it identified only the kernel partition there, and it extracted into a file called kernel, because this is what I defined to be used as a file name. Obviously, in a more complicated format, you might dynamically create the file name. You also have a bunch of utility functions to make sure that there are no path traversals. So if you are using the carving out API, then you don't need to take care of all those problems. Now let's go a bit deeper. I just remove this depth limit. Yeah, I just left debugging on. So in this particular case, we picked up and we extracted the kernel, and it finds all the other things. But there is still another header. If you worked with Netgear, then this HDR0 might be a tell. This is another format that Netgear is using. So what we need to do is create another handler if we want to be very precise. So I just go to step 3 in my journey. Let's quickly check this out. And in this particular case, I also added a TRX header. This is the format name for this HDR0. And I added next to my CHK enteral a TRX handler. As you can see, the logic is very much the same. Just define the magic. I'd already defined the headers. I parse it, and I just define the chunk. So obviously you can add a bit more checks to make sure checksums are correct or of those sizes make sense in order to avoid picking up some false positive. And just to jump there, I also created an extractor for this format. It's very similar. The only difference that the format defines actually 3 partitions. So what I'm doing, I'm just checking out part 1, part 0, part 1, and part 2, getting the offset from the header, and then in this case, basically dumping 3 files. Let's quickly see how it works. So it does the extraction. And if I look at the results, let me quickly go outside. Then here I can see that even the partitions were identified correctly. So again, it helps me to have a better understanding, not just finding some random squash, fs, somewhere down the line, but precisely identify what the files are. Also, if I go back to the previous one, oops. Let's go to the sunburst. Maybe that's easier to see. Then I can see all the partitions and all the details, so I can jump to a partition, understand what's there. So all the visualization just get more accurate. I think with this, obviously in this particular case, like there is no super high need to actually understand these formats, as we could, even without these format handlers, identify the kernel or identify the file system. But in some case, it's good to know like how these are structured, especially if there are some other things lurking there. And obviously, if it's something unsupported, then the logic gets a bit more complicated. I just choose this as an example. Sorry, I just choose this because the file system format is fairly simple, and I just wanted to showcase how easy it is to actually create a format. So we actually created our first handler and first extractor. So just a few words on where we are heading with Envelope. So Envelope is being very, very actively developed. One of the things that we are working on is creating an even cleaner reporting of the extraction process and get basically a result of a summary of like what type of file systems were identified, what type of information, what type of files, what are the unknown chunks. So we would like to work on that. Also, right now, we do not extract too many metadata. So for example, we extract the files, but we would like to also report on permissions, which is sometimes lost during the extraction process, file ownership, stuff like that. Also, we have some plan and we are working on extending the unknown chunks with some auto identification. So for example, if it's a 0-byte padding, to pick it up as a 0-byte padding, so it's not an unknown chunk. If it's an FF padding, pick it up as an FF padding. We also see cases where there are some data in it. So if we can identify some strings in it, or we can identify some logic to automatically pick those up and give you a hint, so it's easier to deal with the unknown chunk, maybe create a new format handler as well. And last but definitely not least, we are continuously working, adding additional formats that we encounter, and we also encourage everybody else to do so. So basically, feel free to contribute, test your weirdest files, report bugs. Everything is on GitHub. If you have any problem, let us know. We are super happy to help you. And we would love to see pull requests coming from the community. So if you find a bug or have a cool idea for a feature, report it, but even better if you just send a pull request for that. So with that said, thank you very much for your attention, and I believe we have a few minutes for questions, or if you want me to double click into any of the details, would be super happy to do so.
Any questions from the audience? Good.
Thank you. Do you somehow deal with encrypted firmware? Like obviously, if you have credentials, but can you deal with the encryption in some way?
So yes and no. I mean, it very much depends on if that could be decrypted. So if the for example, if there is a publicly known decryption key or a password, then it's very simple to create a handler for that. We are experimenting with some formats and building in some encrypted format support. It's a bit different. We have some of those firmwares, but we are not always in the position to actually open source it due to confidentiality agreements. We're also toying with some ideas where we can do some simple brute forcing on certain formats. So, for example, we've seen cases where it's just a zip file which is encrypted, and in many cases it's just a very simple password. So it could be feasible to actually try to brute force it. There are also many projects out on GitHub which is dealing with encrypted format where the decryption scheme is well, get public, let's put it like that. Someone reverse engineered it. So one of our dream, if I want to say so, is actually get those scripts which is lurking around on GitHub and God knows which repo and incorporate into unblob. It would be really cool if all you need to do if you are dealing with a firmware, just run unblob, pull all those format support. I would say right now we are much more limited by our time, but I would say that if there is a particular format, encrypted or non-encrypted, especially if there is a already available like open source or reverse engineer script, it usually takes like a day or maybe half a day, couple of hours to actually port it to unblob, and then really you can have a, sorry, a unified library to deal with. So I think the power of unblob is that you don't need to have many scripts, one script for this, one script for that, but you can unify them into one tool and let it take care. So we would just move it. Generally, we are very open. It's either limited with some confidentiality issue or our time, but otherwise, yes.
Okay, awesome, thanks.
Thanks.
Anyone else? Thank you, Martin.
Thank you very
Thanks,
much.